Objective: to understand black body radiation and quantum theory.
Think it over.
When an iron rod is heated, at first it turns red. As the temperature increases, it turns orange before turning yellow, and then white, and finally blue. Have you ever wondered why the rod does not turn yellow or orange before turning red? Why is light produced on heating solids? Let's understand this phenomenon better. In general, when radiations strike the surface of any body, a part of it gets reflected, some part of it is absorbed, and some bit of it is transmitted by the body. When solids are heated, they emit radiations of different wavelengths. For example, when iron is heated, it emits radiations and becomes dull red, which turns to deeper red with increase in temperature. On further heating, it changes color from red to orange and then to yellow, followed by white, and finally, at very high temperature, it turns blue. This shows that radiations are emitted in the order of increasing frequency. In the visible region, the frequency of red light is lower than that of blue light. On the contrary, an ideal black body is a perfect absorber and emitter of radiation. A blackened metallic surface or a hollow sphere with a small opening, blackened inside, almost behaves as a black body. The radiations that enter the small opening gets reflected within the sphere multiple times until all the energy is absorbed. Hence, a black body is a perfect absorber and emitter of radiant energy. It is to be noted that at a given temperature, a black body radiates maximum amount of energy. It further radiates the same amount of energy it has absorbed. Now, let's take a closer look at the graph plotted between the wavelength and intensity of the emitted radiation. The graph clearly shows that at a given temperature, the intensity of emitted radiation increases with decrease in wavelength. The intensity reaches a maximum value at a particular wavelength and then starts decreasing with decrease in wavelength. At a given temperature, there is a particular wavelength at which the radiation emitted has maximum intensity. With decrease in temperature, the position of this maximum intensity shifts towards higher wavelengths. Electromagnetic wave theory of light could not explain these observations. Max Planck then proposed the quantum theory in 1900 to explain this phenomenon. Postulates of quantum theory. According to the quantum theory, radiant energy is emitted or absorbed not continuously but discontinuously in the form of discrete packets or bundles of energy called quanta. Atoms and molecules can emit or absorb energy in discrete quantities only. The smallest amount of energy that can be emitted or absorbed is in the form of electromagnetic radiation and is known as quantum. In case of light, the quantum of energy is called photon. The amount of energy associated with the quantum of radiation is proportional to the frequency nu of the light. which implies that E is directly proportional to nu, or E is equal to h nu, where E stands for the energy of radiation, h is Planck's constant. The value of Planck's constant in SI system is 6.626 into 10 raised to the power of minus 34 joules second. In the CGS system, it is equal to 6.626 into 10 raised to the power of minus 27 erg second. In terms of velocity and wavelength, energy can be expressed as E equals to hc by lambda, as nu is equal to c by lambda. The total amount of energy absorbed or emitted by a body will be a whole number multiple of the quantum. That is, E equals to nh nu, or E equals to n into hc by lambda, where n is an integer with values 1, 2, 3 and so on. This implies that a body can only emit or absorb energy equal to an integral multiple of h nu, such as 1h nu, 2h nu, 3h nu, etc. It cannot emit or absorb energy which is a fractional value of h nu, such as 1.6h nu or 3.2h nu. This implies that energy can be emitted or absorbed as 1h nu, 2h nu, 3h nu and so on. This is known as quantization of energy. Let's summarize. Energy is emitted in the increasing order of their frequency. A black body is a perfect absorber and emitter of radiant energy. According to Planck's quantum theory, energy is emitted or absorbed discontinuously in the form small packets of energy called quanta. The energy of quanta E equals to nh nu, and this energy is quantized.